Hello students, welcome to my channel Explore Physics, Let's Explore. In the previous class, I have solved few numerical problems based on electric power. Today I am going to explain you about the effects of electric current, what are the different effects and what are their applications in our day-to-day life. We are going to discuss about that. So there are mainly three effects of electric current. And what are these? First, chemical effect. Second, magnetic effect. And third, heating effect. So first we'll start with chemical effect. So here in this particular effect, when the electricity is flown through a solution or an electrolyte, it breaks down into its ions, and that is the chemical effect of electric current. Electroplating is the best example of the chemical effect. Now the magnetic effect. It has been observed that wherever there is an electric flow, there has to be one magnetic field around the conductor. If you recollect in your lower classes, you've read about one activity when if you bring the copper wire or any wire and just wind over a pencil and connect the two ends of the wire or two different terminals of the battery, then the electric current flows through it, and if you bring the compass needle next to it, this shows the deflection, confirming that there is a magnetic field produced because of this flow of electric current. So this magnetic effect, wherever there is screen, loudspeaker, everywhere we can see the magnetic effect of electric current. Then for heating effect, all the heating devices or equipment which we use in our homes is based on the heating effect of electric current. It's been observed that the electric current, the part of it is converted to heat energy. Electric heater, room heaters, geysers, immersion rods, iron, electric bulb. There are different examples of heating effect of electric current which we use in our day-to-day life. So we will be discussing mainly about the heating effect today. So let's start that. So let's talk about the heating effect. You have observed in and around your house the different heating devices, like I gave you the examples of electric heater, geysers, the electric bulb also where the filament glows. So all these are different examples where electric energy is converted into heat energy. And that's the main purpose, because we want maximum heat energy, and that's why we use these equipments. Now, if we have the electric wire, the wire will offer resistance to the flow of electric current, and electric current has to do some work to overcome this resistance so that it will have the smooth flow. So suppose the work done here is W, and the potential difference across the ends of the conductor of the wire is V. The charge, say, is Q, which is flowing through the wire till or for time t. We know that V is equal to W by Q, or W is equal to V into Q. We know that work done is equal to potential difference into the charge, or I can write W is equal to V, instead of V I can write IR from Ohm's law, and Q instead of Q I can write I into T. How? Because we know that because V is equal to IR and I is equal to Q by T. So these two formula I had taken, and I have substituted the value of V and I in this. So I have got the formula W is equal to I square RT. This W, work done, changes into heat energy, and we have the formula, because this is the work done which is stored in the form of heat energy. So this heat, instead of W I am writing heat, H is equal to I square RT. This is very important formula which gives the relation between the heat energy H, electric current, resistance and the time or the duration for which the electric current is flowing in the circuit. This is called Joule's law of heating. So this is called Joule's law of heating. So according to Joule's law, this H is directly proportional to the square of I is directly proportional to the resistance and 3 is directly proportional to T. So we have H, the heat energy, is directly proportional to square of the electric current flowing through the circuit, is directly proportional to the resistance offered by the conductor or the wire, and H is also directly proportional to the time or the duration through which the electric current is flowing in the circuit. If the current is doubled, so it is say 2 times, if it's in 2 times, then it becomes 4 times. The heat energy becomes 4 times because it depends on square of I. So if I'm going to double the electric current in the circuit, instead of I, if I'm taking 2I, so naturally 2I square, it will be 4I square, and the heat energy becomes 4 times of the original value. If I'm going to increase the resistance, say instead of R, if I'm taking 2R, the heat energy also will be doubled. And same goes with time. If the time duration has become double or 2T, then H or the heat energy also will be twice of the original value. This, as I told you, it's called the Joule's law of heating, that H, what does it say? That heat energy produced in a circuit is directly proportional to the square of the electric current flowing through it. Second is heat energy is directly proportional to the resistance offered by the circuit, and third, heat energy is directly proportional to the time through which the electric current is flowing in the circuit. This is very important formula. We'll be solving numerical problems based on this. Please subscribe, like and share my channel if you like the content. So this is about the heat energy or the Joule's law of heating. If you see here, it says H is directly proportional to R. So that shows that if the resistance is more, the heat energy produced also will be more. If resistance is less, heat energy produced also will be less. Keep this in mind. All these 3 points which I have told you, please keep this in mind, because there's so many application based questions which are based on this. So H is directly proportional to R. I've told you, as if R increases, heat energy also increases. Now we'll take the application of this heat energy, or this formula H is equal to I square RT. So the first thing is, it is used to make heating appliances or equipments. It is used to make different heating appliances. For example, if we have the heater which we use frequently in our houses, it has the nichrome wire, because the main purpose of this heating appliances is to give the heat, to give more and more heat energy. So if we have just discussed that for more amount of heat energy, the resistance has to be more. So the nichrome wire is used to make the heating coil, because most of these are using heating coil. So the heating coil has to have high resistance, so most of the energy is produced, or most of the heat energy is achieved or gained through that. Nichrome wire, which when it glows properly, it gives you around 900 degree centigrade temperature. So it glows when it is white, it's hot, or it gives you the, it becomes red hot, it gives you the energy or the temperature. That time it is 900 degrees C. So resistance is more. So resistance is more, heat energy is more, around 900 degrees C it is reached when it gives us the maximum heat energy. So this is first application of heating effect of electric current to make heating appliances. Then the question arises that when the wire becomes so hot but it doesn't melt, then what about the connecting wires? Like for instance, we mainly use the copper wires as the connecting wires, then why can't it melt? Why, when it gives the heat energy, it means then why it doesn't become hot, or why if it starts becoming hot, then the insulation will come off. Why it doesn't happen? Because the copper wire has very less resistance. So very less resistance means it doesn't produce that much of heat energy. So remember, the connecting wires are made up of copper, but the heating coil is made up of nichrome. So this is the first application. The second application is when we use it for the filament, to make filament of the bulb. So the filaments are mainly made up of tungsten wire. So the tungsten again will have high melting point or gives more high resistance, and that's why most of the heat energy is converted, most of the electric energy is converted to heat energy. Its melting point is around 3080 degree C, and when it becomes red hot, it around 2250 degree C, it becomes that hot, and then it starts glowing 2250 to 2500. So around this temperature, it glows. Electric energy converts to light energy. Electric energy heats up the filament. That filament heat is around, the temperature is around 2250 degree to 2500 degree C, and then it starts glowing and gives you the light energy. If you touch the bulb when it glows for a little longer time, you can't even touch it, it's so hot. Okay, so this is the second application of heat energy. The third application is the fuse or fuse wire. So what happens in fuse wires? Fuse wire has very low melting point, and when it is connected in series of the main supply or the main board, the sudden surge in the electric current, suddenly the heat energy becomes so much that the circuit breaks down. So in that case, the fuse wire melts. So it's a safety device. Fuse wire melts and stops the flow of electric current further, and avoids, or all these hazards or different accidents are stopped because of this. So this is also one of the application of electric, the heating effect of electric current. So this is all about the effects of electric current. We'll be taking few numerical problems based on this heating effect in the next class. Till then, stay safe, stay healthy, and a very big thank you to you all. Please subscribe the channel.